Hey everybody, my name is Calvin and welcome back to my channel. Today we're going to be talking about topological sort. In programming, not every sorting problem is about arranging numbers from smallest or largest or names from A to Z. A lot of real programming problems are about order, but not that kind of order. Sometimes, we see that the question is not which value comes first, rather, which has to happen before something else can happen. For example, you can't take an advanced algorithms class before taking data structures. Can't deploy an app before building it. You can't train a machine learning model before loading any data. And these are dependency problems, and dependency problems show up everywhere in the world of software. That is where topological sort comes in. Topological sort is an algorithm that gives us a valid order of items when some items depend on other items. Before we write any code, we need to understand a few vocab words. Topological sort is usually described using graphs. A graph isn't an X and Y chart, rather, here, it's a structure that's made up of nodes and edges. A node is one item in the graph. In our example, each course is going to be a node. An edge is a connection between two nodes. The kind of graph we care about here is called a directed graph. Directed means the edges have some direction. That matters because dependencies are not always two-way relationships. If data structures depend on intro to programming, that does not mean intro to programming depends on data structures. The relationship points in one direction. Topological sort also only works on a directed graph without any cycles. This kind of graph is called a DAG, or DAG, which stands for Directed Acyclic Graph. Directed means the edges have direction, as we touched on. Acyclic means there's no cycles. A cycle would mean something like course A depends on course B depends on course C, and course C depends on course A. That would be impossible to schedule because every course is waiting for another course before it can happen. Let's take a look at our example. Here we have a small course planning example. This dictionary here is written in a way that's relatively easy to read. Each key in the dictionary points to a course, and each value is a list of prerequisites for the course. When we write something like data structures, intro to programming, we're saying that data structures cannot happen until intro to programming has already happened. Our goal here is to return a valid order where every prerequisite appears before the course that depends on it. One valid order could be intro to programming, data structures, databases, web development, algorithms, and then machine learning. That's not the only valid answer, though. Databases and web development could appear before data structures as long as intro to programming appears before them. Topological sort doesn't need to give one single unique answer. It can give you multiple valid answers. Specifically here, the version of topological sort we're going to be building today is called Kahn's algorithm. The core idea here is to find the courses with no remaining prerequisites, put them into a queue, remove them one at a time, and then use each completed course to unlock the next courses. Another key word here to be aware of is in degree. The in degree of a node is the number of edges pointing into it. In this course example, that means the number of prerequisites a course has. Intro to programming has an in degree of 0 because nothing has to come before it. Data structures has an in degree of 1 because intro to programming has to come before it. Machine learning also has an in degree of 1 because algorithms comes before it. Now, let's start coding. We're going to import deck because we need a queue. From collections, we can import a deck structure. We import deck because we need a queue. A queue is a data structure where items are processed in the order that they are added. You can think of it like a line at a store, a queue. The first person in line is the first person that is served. In this algorithm, the queue stores courses that currently have no remaining prerequisites. We've already defined our courses dictionary up here. This is convenient for writing the input, but during the algorithm, we also need the reverse relationship. If intro to programming is completed, we need to know which courses it unlocks, and that's why our algorithm will build two helper structures for us. an in-degree dictionary, and an adjacency list dictionary. And this will take in an input graph in 3. The in-degree dictionary will store how many prerequisites a course still has. The adjacency list dictionary will store which courses are unlocked by each course. We need both because topological sort will constantly update which courses are now available. Now let's initialize both dictionaries with values. We'll write a for loop for course in graph. We'll set in degree at index course equal to 0. We'll also set adjacency list at index course is also equal to an empty list. These aren't the final values yet. We're going to be setting up the structure first so every course exists in both dictionaries before we start filling in real dependency information. Now, let's actually calculate the real in-degree values and build the adjacency list. For course prerequisites in graph, and we'll access our dictionary items using this method call in degree at index course is equal to the length of any prerequisites. For every prerequisite within prerequisites, we'll append its corresponding prerequisite index with a course. Here, this line will count how many prerequisites each course has. If the prerequisite list is empty, the course has an in-degree of 0. If the prerequisite list has one item, the course has an in-degree of 1. Then, the inner loop builds the reverse relationship. The original graph says data structures depends on intro to programming. The adjacency list says intro to programming unlocks data structures. We'll need that reverse relationship because when a course is completed, we need to reduce the in-degree of the courses that were waiting on it. We'll also add in a couple print statements so we can see the result when we're done. Starting in-degree values, and then we'll print in-degree. And we're also interested in the courses that are unlocked by each course. And we'll print our adjacency list. Now, let's actually create the queue now. Well, we can initialize the queue by doing queue is equal to dec right here. Then we'll write another for loop. For course in degree, if we see that the in degree at index course is equal to 0, we'll append the course. If the course has an in degree of 0, it has no prerequisites, so it can go into the queue immediately. In our example, Intro to Programming is the only course that starts within the queue. Let's also add a print statement right here to check for the initial queue. Print list. Here, we're also going to define a variable called result. We'll initialize result to an empty list. This list here will store the final topological order. Every time we remove a course from the queue, we add it to the result because that course is safe to take at that point. Next, let's implement the heart of the algorithm. Step is 1. And then while queue will, while there's items in the queue, do current course equal to queue dot pop left. We'll append the current course to results. Also add some print statements right here, just so we can see the results later. Here we're going to print every step, and we're taking which current course. And then we'll also print the current result. For every next course in the adjacency list at index current course, we'll decrement the in degree at next course by 1. And now, if the in degree at next course is equal to 0, we'll append to next courses. And then we'll also add a print statement right here to confirm that our algorithm here is making courses available as they should. And finally here, we're going to add another print statement to show the value of the queue. As it stands. Here we'll add another print statement to show the queue as it stands. And then we'll increment the step by 1. Let's break this down a little bit more. The line in degree next course decremented by 1 is especially important here. That line represents completing one prerequisite. If data structures was waiting on intro to programming, and we just completed intro to programming, then data structures now has one fewer prerequisite remaining. When the in degree becomes 0, that means all prerequisites for that course are now complete, so the course can be added to the queue. Our final step here is to add a cycle check. If you remember from the beginning, we talked about why we can't have topological sort with a cycle. Topological sort only works if there are no circular dependencies. And we can check that by seeing the length of the result not being equal to the length of the graph. And if that happens, let's raise an error. Then we'll return our result. Now let's actually test our function now. Order is equal to topological sort of our course structure that we had defined. And then we'll denote that. And then let's do for course in order, I'm going to print course. Here we're going to iterate through the result here and then print every course. Let's run this. After running the code, the first thing to look at is the starting in degree values. Intro to Programming has an in degree of 0, which tells us it has no prerequisites. Every other course starts with an in degree of 1, which means each one is waiting on exactly one course before it can become available. Next, the adjacency list here shows us what each course unlocks. Intro to Programming unlocks data structures, databases, and web development. Data structures unlock algorithms. Algorithms unlock machine learning. The other courses don't unlock anything in this example, so their lists are empty. For example, databases and machine learning and web development. Then we'll look at the initial queue. We see that Intro to Programming is the only course with an in degree of 0, so it's the only course in the queue at the beginning. That means it is the only course that we can safely take first. In step 1 here, the algorithm takes Intro to Programming and adds it to the result. Once that happens, data structures, databases, and web development each have their in degree reduced to 0. See right here. And now, we have data structures, databases, and web development within the queue. That means, now that we've taken Intro to Programming, These courses no longer have any remaining prerequisites, so they're added to the queue. From there, the same pattern continues. Data structures unlock algorithms, and algorithms unlock machine learning. Databases and web development don't unlock anything, so when they are taken, the queue simply just moves forward. And then finally, let's take a look at the final order. This is valid because every prerequisite now comes before each course that depends on it. We can see that Intro to Programming comes before data structures. It comes before databases. It comes before web development. We can see that data structures comes before algorithms. And then algorithms will have to come before machine learning. And we can see that this is a valid schedule now. The reason topological sort is worth learning is that dependency order is a very real software engineering problem that you'll encounter. For example, package managers need to install dependencies before installing the packages that rely on them. For example, workflow tools need to know which tasks can run now and which tasks are still blocked. Another example is course planning systems need to make sure prerequisites are respected. Topological sort sorts by relationships. The algorithm is asking a question: which item has no remaining blockers at this moment? Once that item is handled, it may remove blockers from other items. Those newly available items can then be processed next. And that's the entire rhythm of the algorithm. Start with what has no prerequisites, place it into the result, update the items that depended on it, and then repeat until it is in valid order. Thanks for watching, and don't forget to like and subscribe if you found this helpful.